Well, the future is now and the job is finished. So we have all three types of sweeps. We have zoomed out sweeps, narrow sweeps, and those YTF sweeps that took us all those hours to complete, and they're all done now. So let's look at the results. All right, so these are the zoomed out sweeps, and you can see that the signal generator just applies the different frequencies, and you can see the results there. Cool. Now here are the zoomed in sweeps, and you can see it's zoomed right in tight, just with a few megahertz of span, zoomed right in there, and this will give us probably the most stable reading on each of those values. However, there's a complexity. You can see here that the zoomed in peak isn't always, sometimes there's a horizontal line. What's going on there? Well, the answer is that sometimes in order to force the spectrum analyzer to use the desired band, we have to include some extra span above the peak. And while that might give us a little bit of drop in precision, right, not quite as many pixels focused on the exact peak, it's still not going to be very hard to call the top with high precision there. So it really won't affect our accuracy much, but what it does do is when we have a situation with overlapping bands, normally the spectrum analyzer likes to default to the lower band, but if we include some extra span above the peak that we're looking for, we can exceed that overlap range, and we can force it to use a higher band instead. So that's just a little trick that we use so to disambiguate between one band and the other band when both bands could potentially cover the same frequency range. All right, so these were the sweep results, and there are a couple things to note. First of all, this YTF sweep, we saw with our calibration earlier that the YTF calibration values were all very smooth. But if we look here, it says the optimal YTF values are all rough and sawtooth shape. And actually, this is just a result of the built-in YTF calibration not being very good, because it only takes one frequency into account at a time. It makes no attempt to smooth them. And in fact, if you were to take this and program it into the instrument, you would get really awkward results, like you would get zoomed out peaks doubling up as it went past one of the fine adjustment in the preselector went past one of those sawtooths and would bump over that YTF peak, and then you would get this slipping into the image frequency, and it's just a mess. So you don't want that. You want to smooth the YTF and be consistent, not hop between different optima on adjacent frequencies. All right. The other weird thing that we see, well, we see some noise here, but these are just noise. Like sometimes it switches bands, and the first trace isn't great. Whatever. Yeah, we just make the code robust to that when it's building a calibration. But what we see here is we see a little divot. And what's that little divot all about? That little divot we see here right at 24, 25 gigahertz. We see that the zoomed out trace in band 3 is significantly different from the zoomed in trace in band 3, and with the preselector peaked trace in band 3. Why is that? Why is the zoomed out trace so different in amplitude? We're talking about 5 decibels, so it's almost a factor of 4 there in linear amplitude. What's up with that? What gives? Well, the answer is that as we sweep, when we're zoomed out, the YTF has to sweep the entire range of the spectrum analyzer every time it sweeps, and so it's sweeping back and forth, and it's traveling at high speed. Whereas when we're zoomed in, it really doesn't have to travel very much, and so something about that travel is going wrong. Somehow our calibration is working when it has a chance to park, and it's not working when the YIG filter is traveling. So why could that be? I mean, here we see the shape of the YIG filter with different fine-tuning settings across different frequency bands, which is kind of cool. But really, the view that will make it obvious what's going on has to do if we dig into the optimization of the YTF, and so we'll open up our notebook that does that. So here we have we're showing. Again, for every band, this is just showing the amplitude of the YIG filter at its center for the different tuning levels and the fine tuning setting. And so effectively we want to choose the level that peaks this is kind of the idea, but we don't want to jump, if they're different optima, we don't want to jump between them like we've had too much sugar today, because that will result in a bad calibration. So we apply a global optimization here that will, the optimization function is going to, the loss function is going to have both the decibels of loss due to mistuning, but also a smoothness factor, right? We're going to take the derivatives and we're going to of this final trace, and we're going to put that into the loss so that it's smooth. And then of course there's going to be a coefficient between the two that adjusts the trade-off, and we can trade and we can calibrate that. But that's a sideshow, right? I've already done that. What we see here though is that they're rather than having hyper jumping between the sawtooths, we still have this problem where there are kind of two optima in this in band 3, and we see how it really sticks with one for most of the trip, and then it hops to the other one, and that's right where we were having problems in this 24, 25, 26 gigahertz frequency range. So let's look at this a bit more closely and see. So this is the optimization process. We see that as it does more rounds of gradient descent, we see that it in one part it sticks to one hump of the camel, so to speak, and the other part sticks together. Let's get the cross section to show what I mean by humps of the camel. So let's take cross sections here, and since the colors can be a little bit difficult to see, you see indeed there are two bumps here. And the problem that we're seeing is that it switches from the bottom bump. We would like it to stick with the bottom bump, but it picks an opportune moment and it switches over to the top bump. And it's within that switch that we're having the different trouble between, we're having the different behavior between the YTF in motion and the YTF in standstill. And that could just be some smoothing effect with a DAC, or it could be some dynamic effect in the YIG itself. I don't really know, but I do know that we want to stick with that lower peak. And so how do we do that? Well, I mean, the cheap and cheerful way to do it is you just you have it start the optimization process at a different randomized point. So there we go. And if we kind of put the whole curve beneath the entire optimum range, then it just grabs the lower peak every single time, and that's good there. If we were trying really a bunch of different settings, right, we might have to change the objective function to get this to work, but whatever, we could do it. And then the result is this, whereas previously in gray, the old calibration had that jump in band 3, where it switched from one hump of the camel to the other hump of the camel, one bandpass portion to the other bandpass portion. Here we stick with one hump through the entire range of the band, and we expect that to have much better dynamic range. And so we would write that out to GPIB and recalibrate, except actually I have already done that. So the calibration that you saw, the sweep that you saw, was actually the one that happened after I had made that change. So we don't have to wait another 5 hours, because the 5 hours that we waited were the 5 hours after that change. And so we can see we've got a new sweep, can't really see much in there, can't really see much in there. But where we do expect to see a change is here. We don't want to see that divot anymore. And indeed, we see that the divot has gone away. The built-in peaking algorithm is still trash, but the divot has gone away. And now it works whether it's zoomed out or zoomed in, and that's great. That's what we wanted to see. And so the one last thing to do would be to take this new YTF setting and program in the values, the observed amplitude values from in this new section where we adjusted the YTF settings, right? The old measured amplitude values aren't going to be correct, so we want to take the new ones, the new power sensor measurements that we took from this sweep, and we want to program it into the device. And that's exactly what we did down here, because actually I lied again. This isn't the sweep where we took the updated settings. This is the sweep after that, where we confirmed that those settings stuck, and indeed they did stick, and we got really good consistency. So that's how you calibrate the 8560 spectrum analyzer using my notebooks. I'll upload those to GitHub and put the links in down below. That's all for today. Bye.